folks. Okay, well, this time we wanted to take a look at code generation for functions, for function calls specifically, and for the returns. So we talked earlier about kind of the division of responsibilities between the caller and the callee, and most of that from a code perspective is relatively straightforward. Right? If you're going through preserving and restoring registers, you're, let's say, pushing them on the stack and popping them off the stack. Nice straightforward sequence of operations. If you're setting up and retrieving return values, you're pushing space forward on the stack and retrieving space from there when you pop it off the stack. When you're setting and cleaning up parameters or local variables, again, you're pushing data on the stack and popping it off afterwards. Right? Transfer of control, you're storing the return address someplace and then setting a new value in the program counter, for instance. It's all relatively straightforward operations from just a straight let's generate the code point of view. The questions are going to come in terms of, well, specific code for specific operating systems, obviously for specific architectures, depending on the assembly language instructions you've got available to you, and in cases where you're not actually dealing with a runtime stack, then again, obviously it's going to be a little bit different, but still relatively mechanical. The interesting issues are going to come when we start looking at some optimizations. So we'll discuss some of the ideas now and then get into gory details of optimizations in the optimization section. All right. So a few of the things that you might wind up looking at are saying, okay, well, if we figure out how often a function is called, if it's only called once, then it might make more sense to just replace wherever that function call is with the set of code, with the instructions that the function would actually run, essentially inline the function. Right? So that might be much more effective than setting up the process to do a call and return for something that's only going to get used this one time. One of the other things you can consider is in that division of responsibilities between callee and caller, anything that the caller does has to happen on every single call to any function. Right? It means that if you've got 600 function calls, it's happening 600 times. Right? It appears in your source code 600 times. So if there's 600 different places that is where you make a function call, then for each of those locations in the source code, that transfer to and from has to happen. If some of that code can be moved into the callee instead, then those instructions only have to appear in the source code for the callee in that one spot, right? And it's automatically going to get run every time the callee is run. So you can reduce the sheer size of your source code by moving some of these operations into the callee from the caller. So one of the ways that you might wind up doing that are essentially to have the caller somehow provide the information to the callee and let the callee deal with the results there. So we'll talk about that with the register preserves here. So in that division of responsibilities, the whole idea of sort of saving the caller's registers, making the function call, and then restoring the caller's registers so they don't get corrupted by the callee can involve a lot of code if it's happening a lot of times, right? If you've got a lot of different places where you call functions and all of them are saving these registers and then restoring them, and if you've got a lot of registers that need handling, then that's an awful lot of code repeated in an awful lot of places. So one of the ideas is to go through and say, well, we can take advantage maybe of some hardware instructions. Some systems actually provide you with instructions to save or restore a whole bunch of registers at once. So, load this range of registers or store this range of registers into memory. So that might help some. Another idea is if we can have some kind of compact mechanism for the caller to give the callee a list of which registers to save and have the callee do it. Right? So again, you're pushing that responsibility into the callee if you've got a compact mechanism for letting the callee know which ones it should be doing this with. The other possibility is to have the compiler generate a special function to do the saves and restores, or a special subroutine to do the saves and restores. But since this is something that's only getting invoked by the compiler, this isn't like a general purpose function. This is something that the compiler is just using to go through and do the saves and restores before a regular function call. So the compiler could create a sort of specialized, streamlined routine that does these saves and restores with special rules to call and return from this specialized routine, right? So that you get this sort of high efficiency routine that whose only purpose is to go in, save a bunch of registers, or go in and restore a bunch of registers. So that is certainly a possibility. And again, what would happen is at each function call, you simply invoke this routine. And it might even be the case that the callee invokes that routine right at the start and invokes the restore routine right at the end. So that, again, those calls come in the callee and not the caller, and therefore are replicated less often in the source code. Right? So there are things you can do to try and improve this. Now, parameter handling is one of the things that we haven't talked about too much. We talked about the idea of pass by reference and pass by value. If it's pass by value, you have to evaluate it first and store the result someplace, probably in a register to be communicated to the callee. And eventually maybe pushed on the stack in whatever the parameter space happens to be. If you're doing a pass by reference, then you've got to make sure that the thing that's being referenced is actually in memory and up to date at the correct address. One of the things that crops up, though, is if we are going through and doing, let's say, a pass by value where we're evaluating all of the parameters and communicating those values to the callee, what order should we actually evaluate them in? Right? If we've got 10 parameters for a function, what order should we evaluate those parameters in? Because the evaluation of those parameters might involve side effects that would then impact the computation of other parameters. So the source language might specify the order you have to evaluate them in. So in that case, you've got no choice. It's, evaluate them in this order and pass the results. But if the source language doesn't specify that, then the compiler's got to pick an order, left to right, right to left, pick some kind of an order and then apply it consistently. Right? So this is where we need to figure out how side effects are going to play into the order of operations here. So I want to take a look at an example. So we'll take a C function and pass it a really demented bunch of parameters here. So we're going to have I guess this is actually a C++ function because I made it pass by reference, didn't I? Okay, so we've got a C++ function here where the first parameter is passed by reference, and then we've got a whole bunch of by value parameters. And all the function's going to do is print them all out so we can see what actually wound up getting passed. And then we're going to have a statement. Ooh, I wanted to change that to an A++. So what I wanted here, and the source code that I actually executed and showed you the results of, actually has this as an A++, so an auto increment. So I will fix that slide. So what we're gonna do is assign A the value of A++. So do a post increment on A, assigning the result to A, and return that. And in the caller, whatever comes back, we're going to assign to some variable A. And what we're going to pass is essentially this one parameter A over and over and over again, but we're going to do things with side effects as we go through this list so we can see what order it actually evaluates things in. So we're going to pass just regular old A, because that first one is passed by reference. So this is the one that's getting modified inside the function itself. We're adding 100 to A to pass the result. We're pre-incrementing A by 1 to pass. We're decrementing A by 20 and passing. We're passing just regular old A. A post-decrement on A will pass, and we'll pass A itself again. So, if you were faced with this, right, if somebody just showed you this chunk of code and said, what's it print out? What values print out inside the function, and what value prints out at the end? So now we have to go through and say, well, which of these things gets applied in what order? And if I'm doing things like this, if I'm doing things like A minus minus, because it's a post-decrement, does it happen sometime during the process of evaluating all of these? Or since it's a post-decrement, does it mean it actually is supposed to happen after the function call? Or this is kind of an idea. Or if this is and again, this is supposed to be an A++, if we've got a post increment here assigning that value to A, what happens with that value? So, let you stew on that for a second and think, what would it actually do? What would the value of that first reference parameter be? Is it going to do these things, let's say left to right? Is it going to go through and compute, so A was 1, so is it going to pass 1 and then say pass 101 and then pass 102 and then what would that be, 82, is it going to do the post decrement and pass an 81, or is it going, so is it going to do the decrement and pass an 81, or is it going to pass the 82 and then do a decrement? And so there, is it going to do the 81 from that? Right, so that would be assuming it goes left to right, or the other way around. Does it go through and pass a 1, either a 0 or a 1, depending on what order it does that decrement? Let's say a 0, what would that be? A negative 20, negative 19 if we go up by 1, whatever that's going to be, an 81, an 81. Right, what are we going to actually wind up with? And again, if you're a programmer just looking at something like this, you have to look at that and go, wonder what it's going to do. And in point of fact, what this one actually does, so here I actually had the code that we actually wound up running, so here it actually has the correct A++. So, same chunk of code, and the output actually comes out as this 81, 81 negative, so 81 for that, 81 for that, negative 19 there, I think that's supposed to be a negative 20. Yeah, it's got to be a negative 20. A 0, a 1, a 1. So here, since A started off at 1, it's got to be going right to left, right? It's past the 1. And then with the post decrement, it passed a 1 anyways, right? A 1 got into the function. So this has to have done the 1 and then decremented. And we see that with the next one, where it actually got the 0, and then the negative 20, and then the negative 19, and then it's up to 81, and still an 81. And then it returned the 81. So we didn't get the impact of the plus plus here. So it had to have assigned the value of A to A, so just left A at 81, and then did the increment, but it returned the result of that assignment. So it returned the 81. So again, it's not always obvious from the source code, if you don't know the specific rules of the language or the specific rules of the compiler, what the result is going to be. And actually, with a couple of the operations, if you go through and compile this, with a couple of these operations, the compiler, so this was using G++, the compiler will actually spit out a warning saying that some of these results are undefined, which means that the compiler recognizes that in a couple of places in here, the results of the operation aren't specified by the language, and so the compiler just made something up. Right? It picked a set of rules. So again, there are things that a language won't always specify for what order to do things. And there are a couple of examples in here. I think it was regarding the post increment or pre-increment and post decrement, I believe, if I recall correctly, were the operations. It might actually have thrown out warnings about a couple of the others as well. But again, this is something to be aware of, right? The impact of side effects and the order of evaluation of your parameters. All right, just the last couple of things I wanted to mention about the parameter passing side of things. It's entirely possible that whatever functions or whatever parameters the programmer actually specified are supposed to get passed, the compiler might add more. Right? There's additional information that typically the compiler wants the callee to have access to, and it's possible that the compiler will add some of those as parameters. Again, it depends a little bit on the specific system that you're working on as to whether some of these things go in specialized registers or whether there's a predefined set of rules for these things. But anything else, the compiler is quite likely to say, okay, well, I'll pass it as a parameter then. So this might include things like, a pointer to the callee's activation record, right, where it is in the stack if you're using stack frames, a pointer to the caller's activation record. Maybe the return address might wind up getting passed as a parameter. Again, something might get pushed on the stack, or it might be passed as a parameter. There might be extra addressing information that needs to be passed. So we were talking about the idea of having nested function declarations where one function is declared inside another. So the inner function needs access to the outer function's variables and parameters and whatnot. So it needs access to that one's activation record. So it's entirely possible that you might have additional pointers passed to give this extra addressing information. If you're looking at an OO method, then it's very common to actually pass a pointer to the data for the object that's being manipulated, right? So the idea of the this pointer in C++, where you're passing a pointer to the struct, if you like, that's got that actual information in it. If you've got a higher order function where you're passing functions as parameters, it's entirely possible that you can't simply pass a pointer to the code for the function. There has to be, that's being passed as a parameter, there has to be additional information about that function passed. So maybe you put together something like a descriptor for the function and pass a pointer to that. Right? So there might be all sorts of additional parameters that the compiler throws in for either specific circumstances or based on the nature of the language that you're compiling. All right, and again, a lot of this comes back to what the expectations are from a sort of operating system and assembly language point of view. What's actually supported, what's built in, what are the rules that you have to live within, and what do they provide you, and what else are you going to have to come up with on your own as a compiler. So I think those were the key points I wanted to bring up. Yeah, we'll take it from there next time.